Now, wherever we talk of these functions, the spectral or the temporal phase, and we are discussing them pretending as though we know everything about it at all time and at all frequency. But we must at some point reconcile with the fact that these are quantities to be either measured directly or measured or inferred from primary measurements in one of the two domains, be it frequency or time. So as such, it's a bit of a catch-22, as can happen in physics or engineering, that we hinge our entire discussion on a quantity which we may not know a priori, but we just give it a definition, a robust definition, and develop the framework, and then worry later about how to measure it. This is exactly what happened even chronologically with femtosecond laser pulses, and carried over to its offspring, attosecond pulses, because of the very simple conundrum and puzzle and question that if we have created the shortest events possible to be created by man and somehow even entered it in a book of records if you choose to do so, and how did you measure the shortest event, right? So you need typically an event or something controlled on durations which are shorter than the shortest event, in which case the shortest, using the term or adjective shortest, loses meaning, right? So therefore it was quite an effort uh, in in science, technology and engineering to come up with ways in which we can measure these shortest events. So in essence, we need referencing techniques had to be developed where the reference was sort of inherently, I mean, we had to do some kind of self-referencing. Reference had to be derived from the same test signal which we had for the measurement, right? So keeping all these details in our mind, we ought to think about these phase functions in the time of spectral domains in the spirit and sense of Taylor series. Phi of t is essentially uh, a series of terms of increasing order where the first non-trivial um, phase component is d phi by dt, which is related to the instantaneous frequency, which we just discussed about a while ago. And the higher order terms will have their own sort of meaning, right? But then, as I'd emphasized also in the earlier lecture, measuring or rather describing these in the time domain is not of much consequence for exactly the same problem that I brought up. These are really very brief intervals in time. So a very brief history of these pulses in time. They're very difficult to measure as such. Okay, now today when we have well developed techniques, it seems as though this was obvious. That's not certainly the case. In fact, all these quantities relating to the phase are measured in the spectral domain. So that's where we begin this week's lecture or interaction, where we really ought to peg all our insights, reference, and everything we have to the frequency domain. This is our go-to domain here and hereafter. The time domain description of any of these quantities typically then comes out as something deduced from frequency domain measurements. Measurements or metrology holds the key, and that we do in the frequency or frequency wavelength domain, or I should have more appropriately called it the spectral domain. In the spectral domain, which is just as complete and legal as the time, the key player is the spectral phase function. We ought not to be tired of reminding ourselves about the importance of this key player, the kingpin, in our description. Okay. And once again, we use this function in describing the pulse even before we measure it. Right? It's like a credit card, essentially. In the parlance of modern finance, use it, then think about where this where the source comes from. Right? So then we have to think about it incrementally thereafter. The first phase term is phi naught. It's not insignificant. What is phi naught? We will look at it. Okay, but this is nothing but we have already encountered this. This is the absolute phase, as we had called it once. Or we had called this the initial phase. Phi naught has units of just radians. If I subscribe to the frequency variable omega, and it's got to be the same whether in time of frequency domain. It is independent of time, it's independent of frequency. The nice thing is if ever I have to measure phi naught in whatever way, if I measure it in the in the frequency domain, it stands for itself in the time domain as well. But then the first derivative of the phase function phi of omega with respect to frequency, indeed now we need to distinguish this phi 1 in the frequency versus the time domain. The Taylor coefficient phi 1, the first order coefficient, is essentially the frequency derivative d phi by d omega at omega naught. This is what we call the group delay. We described this. We gave this the name or the symbol T sub gr. Any variation of a quantity with respect to any frequency, angular or cyclical or whatever, is synonymous to the word dispersion. So when I say variation with respect to frequency, it could also be wavelength. A variation in the spectral domain is typically called a dispersion. Colors are dispersed, right? Likewise, the dispersion of energy is another common thing in physics and engineering. So this dispersion of the group delay, this variation of the group delay in the frequency domain, that is the derivative of d phi by d omega with respect to frequency, is called the group delay dispersion. So this is d2 phi by d omega 2, or the second derivative of phi with respect to omega. Note, and I must make this point at some time in this course, that I rather would want to call this as d2 phi by d omega 2 rather than d square phi by d omega square. Or likewise for the cubed, d3 phi by d omega 3 rather than d cubed phi by d omega cube. The simple reason being this is still a linear operator. So calling this the square or the higher order phi 3, calling it a cube, is a bit of a misnomer. All these are linear in their operation. Ergo, if I had, for whatever reason, maybe two pulses maybe produced by the same source and interfering or whatever, I can calculate a summed up group delay dispersion for example, right? So in that sense, we should either call them second, or you can call it the double derivative, whatever, but we should be true to the fact that these are linear quantities. Of course, the point being that, as in all cases, these coefficients need to be appreciable over the spectral region where the spectral phase, the spectral amplitude has appreciably uh, larger than zero, or it's not negligible. So the spectral region where the spectral intensity or spectral amplitude is non-negligible, we need to compute or measure phi of omega and phi 1 or phi 2, uh, as the case may be, which are functions of frequency. If phi 3 is essentially as a very freak or negligible frequency dependence, we might as well toss it out, right? For the pulses that we had earlier called well behaved, we wouldn't need more than a couple of Taylor coefficients to describe them. So very often in literature, and I bring up the point for the following reason, that if we have a good quality of laser pulses femtosecond, it would be sufficient to, you know, deal with only the group delay dispersion. Okay, or or conversely, we want to manage dispersion, or we have to manage this dispersion, right? We have to do this in fiber optics, dispersion management, right? There are such things as dispersion compensating fibers, right? So what are these elements? So these are elements which are managing dispersion for us, and those often also are made up of materials, and the group delay dispersion is also a material property. So you look for materials with a positive GDD or a negative GDD and so on, as the case may be. But then what we ought to do is, for a system, manage dispersion such that we have elements with appropriate GDD values, and then keep the pulse to a reasonable limit where we don't need to invoke higher order dispersion terms, that is terms such as phi 3, because higher order dispersion is more, tackling higher order dispersion gets more and more challenging as we go on. So this is something which we will encounter in various forms, in aspects such as managing the chirp of a pulse, or the very famous chirp pulse amplification, which was the subject of the Nobel Prize in Physics for the year 2018. Right.